I'm going to get started. So I'll introduce myself. I'm Matt Disney from the University College London, and I'm kind of representing work here that's been led by my colleague Lewis, and those of you who know him. He apologises for not being able to be here. The circumstances dictated he very much wanted to be here, and I'm very grateful to the organisers for allowing me to come here and potentially misrepresent some of Lewis's ideas. So what I'm going to talk about then is some options for Earth observation, land data assimilation. A little bit of a vision of what we've learned from trying to do this over the past few years, and some of the questions that have arisen in doing that, some of the things we've learned, and perhaps many more of the questions that remain unanswered, and how we go about answering some of those questions. And I'm very grateful to contributions from other colleagues, particularly Jose, who's over there. So any of the very technical stuff, I'll direct your questions at Jose. Just as a background here, one of the things that I'll be showing is Lewis's new kind of land data assimilation scheme, which allows you to remove all the clouds from the UK. And as we know, that is nothing short of miraculous at the moment. So through the power and the magic of data assimilation, you can turn this kind of white-grey mass over here into this gorgeous-looking summer country landscape here. And this is early in the year as well, so even more of a miracle. So the outline is, and I'm going to talk about some of what we've identified as some of the key issues for land data assimilation. And I'm going to touch on this issue of the balance between having potentially too much information, where that information is perhaps very indirect, given what we want to actually model and observe, and maybe not enough information to do with the key processes that are important. And I'm going to talk about the priors that we need to introduce to constrain the observations in terms of combining observations and models optimally. And as I said, I'm going to cover an overview of what we've learned from various different projects and approaches to this over the past few years, some new methods, and maybe some suggestions for maybe not methods, but approaches that we need to think about as we're moving towards a kind of operational land data assimilation scheme. I'm going to use this quote, and I apologise for those who've seen it before. It's a quote that I use time and again because it does represent the data assimilation problem in a nutshell. A model is clear, desirable and positive, but no one believes it except the person who wrote that model. And data are messy and exact things which are already believed. Everyone believes data except the people who collected those data. And that was a quote from Harlow Shapley, who's an eminent American astronomist, from his autobiography, where in astronomy they have a very particular problem in relation to data and models, in as much as there's almost no data, and so there's a proliferation of models which have extraordinary levels of complexity and the impossibility of ever being able to test them with a useful measurement. Shapley later kind of refined this to say that a good theories will crumble and die, but a good observation will last forever, which is something else to bear in mind. Of course, Shapley was very wrong. He thought there was only one galaxy in the universe, and he spent a lot of his time trying to bring down Edwin Hubble's description of the multitude of galaxies. So don't take everything he says for true. So this issue then of the amount of information that we have, the whole process of data assimilation as a method to constrain and to use information optimally, to understand the land surface, to make predictions and to extrapolate. We have a huge range of increasing satellite data, and the challenge is to use these data coherently and optimally. And I'll come back to what I mean by coherently over the remainder of the talk. But in general, what I mean here is in terms of consistency of processing, consistency of assumptions in the interpretation of data. I mean, that's a huge issue that becomes more and more clear when you try to do data assimilation, is the conception of what we think of as being well-defined parameters between remote sensing data sets and then between remote sensing and Earth system models. That consistency is very often not there or is lacking. And that makes a big problem from an assimilation point of view, simply because you get different answers because you start from different assumptions, even about something like leaf area index, which appears to be well defined. And so one of the things, again, that I'll kind of highlight is this need, if you like, for pre-processing that we already do in remote sensing. I'm coming at this from a remote sensing background where, let's say, we know that what we do in remote sensing is very far removed from the kind of process modelling that we want our data to be able to influence. So we make measurements at the top of the atmosphere of photons and so on, which is of no use to man or beast, and we have to turn those into something that relates to the land surface, that relates to models, and that relates to ecosystem understanding. So we have this kind of common process to go from these raw measurements, which, as I say, are well understood and well calibrated, but very indirect in terms of what we actually want to measure. So we need to do all this kind of pre-processing to extract the kind of physical quantities that we want. So even reflectance or brightness temperature in the thermal or backscatter from radar observations. These are things that we can do fairly well at one remove from a direct remote sensing measurement without introducing too much uncertainty. But again, these are not things that people are really interested in directly from a land surface model carbon assimilation point of view. But even in order to do these things, we need to introduce atmospheric correction, we need to do radiometric normalization, and all these kind of background things that go on before we can do something useful. Then we need to do something useful, which is interpret those observations. We can do that via empirical models, or we can do it via physical models of the radiative transfer process to give us some estimate of the land surface parameters, things like leaf area index, stem volumes, soil moisture. Now we're talking about things that are used to drive, to test, to constrain models, and are related to ecosystem processes. And the point I kind of want to make and re-emphasise is this issue that to combine observations, that these 1 and 2 must be consistent. These things need to be consistent, ideally, so that there are no inconsistencies introduced in from this pre-processing to this interpretation stage, which can easily happen. So, too much information or not enough. So, the Earth observation data, as I said at the outset, are not generally particularly informative about lots of the process that we're really interested in. And we can't always fully retrieve the land surface data, very rarely. It's an ill-posed problem. And a key way to kind of tackle this problem is through using Bayesian approaches and multivariate PDFs to describe the system. But in this case, then we need prior information. Obviously, if you're going to take a Bayesian approach, one of the key aspects is to make your priors explicit. And so I'm going to talk a little bit about priors here. This is very important. So we can use, if we're going to use the information that we've got to the best way possible, we can make use of climatologies, we can make use of expert opinion on PDFs of parameter values. Elicitation, and there's a sort of growing field of research, particularly in things like climate modelling, based on elicitation. Why choose one particular default parameter value of a large-scale model than another? We can do sensitivity analysis and so on, but elicitation is essentially getting people in a room and saying, where's your prior value on this distribution? Where is your prior? Also pragmatic priors, using spatial and temporal correlation. But these priors must be consistent as well. We know that even basic things like different radiative transfer model assumptions between our parameter retrievals and the land surface model use introduces uncertainty, which is very hard to characterise in a data assimilation sense. So the prior model octopus here, thanks to Peter for this slide, but how do we make these priors? The priors that we have with our processing from Earth observation data, commensurate with land surface models, dynamic global vegetation models, better constrained priors reduce the uncertainty in our data assimilation products, or at least help us better understand where that uncertainty arises. Does it arise from the observations? Does it arise from the model? And we know that there's a lot of ecological data that's being made available, as Jens showed through, for example, the TRI database, that we maybe ought to be thinking about using in terms of constraining priors. So to reiterate that, there is quite a lot of information out there. Can we use trait relationships as priors? There's some globally consistent correlations, as Susan and Jens showed already this morning, that represent these kind of adaptation, acclimation, evolutionary trade-off strategies that might well allow us to make some quite strong constraints on some of our priors, and that's something that we should be thinking about in a data assimilation scheme. But we also need to understand how we can put uncertainties on these things, because that's again a key part of the assimilation process, is being able to quantify the uncertainty in our observations and feed that through the process. So various different trait relationships there, and what about trait distributions? As Jens also referred to, there are global distributions of traits that are constrained by relatively well understood observations and for various different conditions. Some vary predictably in time as well in terms of seasonality and so on. And so this is specifically very interesting. There's the slide that's already been seen a couple of times this morning, and this within and between plant functional type variation that is available from the kind of tri-database approach. And I think that's a very powerful tool to enable us to start putting some constraints into data assimilation schemes that we haven't really utilised fully at the moment. So one of the issues there, and I think there's some very powerful constraint information, and of course if you go and ask ecologists about, you do an elicitation exercise on where are your priors for these particular land surface model default parameters, what you'll get is some values out of these distributions here. But exploiting it consistently may be tricky, because there may be indirect information content, it may be biome specific, there's quite large variations within these plant functional types already, and it may be discontinuous. So how do we represent these pieces of information in an assimilation scheme? There may be weak correlations, but we know that one of the things that a data assimilation scheme is good for is for transferring indirect prior information into something that maybe our assimilation scheme can use, into things like transferring from LAI to pigment and water and so on. And there's been some very interesting work related to this, I think, over the sort of recent times by Thomas Kaminsky and Peter Rayner and various other people, but this is a really good example using the CCDAS, the Carbon Cycle Data Assimilation Scheme, to show the strengths and weaknesses of particular observation types and sampling design. I think this is a really key piece of work. And it shows that for given observation types and for spatial locations of observation towers, flux sites, what your benefit is in terms of reducing NEP uncertainty, for example. I think that's the key type of work that needs to feed into thinking about how we're going to do EO land data assimilation more generally, is our ability to meet this kind of work and say, okay, how can we use this information better? One of the things that I think we've been struggling with, and I can see from some of the other work that's been going on, is this issue of model structural uncertainty. Is a given model or a particular approach, modelling approach, capable of predicting the observations? And if it's not, then why are we using that? What's the problem? Is it the problem in the model? Is it the problem in the observations? Identifying this issue of model structural uncertainty is really important. I would say rarely considered. Obviously people consider it, but in general they sort of think, okay, maybe that's a problem for another day. I'm going to carry on updating my model, or I'm going to use a different set of observations, or if I'm an observational scientist, I'm not going to use that model because it doesn't agree with my observation. It goes back to Shapley's quote at the beginning. People will tend to fall one side or the other, rather than considering where these models and observations are consistent or inconsistent and why. So work needs to be done on this hypothesis testing of model predictions, understanding whether a given model or modelling structure or modelling approach is actually suitable. And it was very interesting to see
Lena's talk, where she was addressing that issue of whether this model is capable of dealing with certain types of behaviour. There's an interesting paper by Smith et al. Looking at the structure most consistent with observations, where they're saying, hey look, we're model agnostic here, which bits of this model are doing well, which bits are not for various different models. And they're showing that, obviously some parts of the models work really well, and some parts of the model there's very, very large amounts of variation depending on which of the parameters that you've got observations for and how good those observations are. So there were parts of the models that were working well and parts of them that weren't. No surprises there really, but in a sense, doing this before you start thinking about data assimilation is a key aspect of this, I think. One of the things, the sort of suggestions that arose out of this is Peter van Boddikom's work and the work of others here, is thinking about this sort of issue of PFT versus trait-based approaches, and looking at this trait-based information to say, okay, well maybe this is a better way of representing vegetation types and responses in these kind of models if we're going to do data assimilation. It depends on what you want to do with your model, obviously. So there was his kind of blueprint for a PFT-based kind of approach down to a trait-based approach where you have this kind of habitat adaptation, plant trait information coming in here, and you're clustering your plant response information based more on this trait constraint here, which, if you like, is a constraint that's going in the modelling scheme in the first place, but it's to try and use this ecological trait information that we have more effectively. So we have in the past looked at doing data assimilation and said, well, one way to do it is, because we need to know about the uncertainty in the observation, from a remote sensing perspective, if we use top of atmosphere radiance, we can characterise the uncertainty in top of atmosphere radiance well. Characterising uncertainty in products derived from top of atmosphere radiance is much more difficult because of the subsequent layers of models and assumptions required to go from one to the other. So we have kind of advocated that that's a good place to start in some respects, and from the uncertainty of the observations it is. The problem is that people who are using land surface models have no interest at all in top of atmosphere radiance. So you have to do all the work in translating the land surface model representation through a radius of transfer scheme to something at the top of the atmosphere. So in a sense you're just transferring the problem from other people to yourself. And that's never a good thing. So the issues is, so maybe using the kind of derived products is fine, as long as, and it's much easier, and it's much easier to include in modelling work if the uncertainties can be propagated in a transparent and obvious way, and that's the if really. And one way to do this, if you like, is choosing radius of transfer models, observation operators that are chosen with a particular land surface model formalism in mind to try and keep these things consistent. So this is an example of some work that Lewis did just recently, if you like, to build a kind of toy land surface data assimilation scheme, a kind of what-if version of it. This is for surface reflectance, which it's not top of atmosphere, but it's not LAI either. It's sort of, if in complexity, it's somewhere in between. Gridded surface reflectance products are required for quite a lot of things, many of them include deriving other products from them. But again, we're a little bit more comfortable from an EO perspective dealing with this aspect of it because we can understand the uncertainties perhaps better. But it's a kind of starting point. The idea was to have data from any kind of combination of sensors, so in terms of bands and spatial and temporal sampling. It shouldn't matter. We should just be able to throw it all in the pot and just say, okay, well, if it's going to constrain the process that we're interested in, fine, just chuck it in, as long as we've got the uncertainty on it. What does it do to our model prediction? And the outcome of this was to try and give the best possible estimate of the surface reflectance given all the possible observations that are available. So we're going to end up trying to produce a gridded best estimate BRF product here that we could make easily and freely available over given spatial and temporal support, over all wavelengths over the solar spectrum, with, importantly, a per pixel uncertainty. That then is the next step to allowing you to combine this with a model in an assimilation scheme. There's lots of different applications for this kind of thing. And this is the BRF, but the question is, can we do this more generally? So Lewis's typical approach to this, obviously given his kind of background and interest, but using linear models throughout. So there's a heritage of this, and of course it keeps things simple, makes life easy. One of the things it allows you to do, it allows you to do error propagation properly, which again we would argue is a key part of this. Other useful things, it makes it easy to couple to the atmosphere, and there's a whole bunch of other things that fall out of this that are very useful aspects of a linear modelling approach. So we map all the data to a common spectral basis, we apply a Kalman filter forward in time to help remove outliers, and then backwards in time. So you end up essentially with a Kalman smoother process for this. And what you end up with, so this is my nice map of the UK and northwestern Europe with no clouds and no snow. So let's test it somewhere difficult. So let's test it over England in January, somewhere cloudy and snowy, and the byproduct of this is you end up with a snow-free, essentially cloud-free surface reflectance and then albedo product, which is your best possible estimate given priors and given your use of all the available data. And so you end up this with, first of all, you get very, very good outlier detection. Okay, by doing this kind of forward and backwards processing and considering the uncertainties, you have an expectation of what the surface ought to look like, and then if it looks slightly different, it's either clouds or it's snow. So this is the beginning. This is the beginning of the year. Oh no, so that's more towards the middle of the year. We can end up. Well, you can end up with a snow cover product. What would this land surface look like if it was all snow contaminated? Because we know what the surface looked like when it was contaminated with snow. We just chose to remove it. What does it look like when there's no snow there? So we end up with this a product that I showed you at the beginning, which is essentially our best estimate of the surface reflectance given the observations that are available to us with known uncertainty. So, practical issues then. Observation operators, the radius transfer models that allow us to translate between an observation and a property of the land surface are often slow, computationally demanding, difficult to use. There's been lots of different approaches using lookup tables and artificial neural networks. Some new work on this I think that is very interesting because it's fast. Fast is good if you want something operational. It's using emulators, statistical approximations of the models which help you to quantify uncertainty. Again, emulators are being widely used with large-scale models in climate kind of applications where they allow you to do parameter sensitivity analysis by emulating the full model using a statistical sample of runs. So in combination with things like Gaussian processors where we can run the model many times and we can do these kind of sensitivity and parameter sensitivity analysis rather quickly, Gaussian processors and emulations turning out to be, I think, a very sort of fruitful avenue for moving forward in using potentially still quite complex radiative transfer models, but fast enough that we can do assimilation with them. So I'm going to just skip over this, but this is, if you want to see the details of this is work coming from our ESA-funded project, the EO Land Data Assimilation Scheme, an efficient data assimilation scheme. Jose has a poster on this. And there's some really interesting results that Jose's showing trying out these kind of Gaussian process emulation tools for building in more complex radiative transfer models into this assimilation scheme. Jose's work, he's built a Python library as a sort of template for this, and this is one of the sort of main things that we're trying to do at the moment, is build a scheme. So not one particular model or one particular set of observations, but a scheme, a framework, a set of tools that will allow other people to hopefully come along and plug in their particular model and set of observations to do the same kinds of things. So there are various different choices of radiative transfer model that we can have in here. And this is just some example results that Jose will show more of on his poster of emulating visible and near infrared white sky albedo to show that, again, the emulator is a very quick way to have a representation of a full ready-to-transfer approach that allows you to couple two observations in a consistent way without having to do the full model inversion all the time. And this is full spectrum pro-cell emulation, so across the whole spectrum here. And you can then do, of course, very useful synthetic experiments where you synthesize various different data sets. What if I had these data? What if I had Sentinel-2? What if I had, sparse observations? What if my cloud cover was more frequent, less frequent? You can do those kind of what-if experiments to retrieve land surface parameters using this kind of approach. What we're lacking here, and I think that was something that Jose wanted me to bring up, is the kind of detailed multi-year field measurements over particular different sites that would allow us to test these kind of things better. And that's, there's the kind of validation work that's ongoing with various groups is really important to this. You can also use these kind of approaches to look at spatial autocorrelation, and this is again work that Jose will show on his poster using, this is synthetic, but showing you can use the spatial autocorrelation as a constraint for your data assimilation process. So, in summary then, the sort of operational data assimilation requires this kind of approach, perhaps, but extended to things that are of more interest than just surface reflectance, to real biophysical products. We also need to really demonstrate the benefits of this. If we're going to encourage people from both the observation and modelling communities to go down this kind of route, we need to demonstrate the benefits. What's the added value of doing this? Why should I? One of the benefits is this ability to treat different observations, not just in the optical domain, but in the thermal, the microwave, passive microwave, traits inventory. Throw the whole lot in. If we can show a mechanism for doing this, then I think we're really starting to make progress. And consider what the landscape scale models approach is all the way through the process, not just bolting on the radiative transfer model, but thinking about what the assumptions are that are common, different between those two sides of the problem. So, transparent, consistent treatment of uncertainty, very necessary. So there's lots of work pushing this forward, various different groups and so on. And that's one of the questions that we kind of, arose out of this, that how do we encourage these developments across agencies, models, communities? There's a lot. Developing tool sets for doing this is one aspect of this, but there are clearly many others. So, thank you very much. One question? Anyone have a question?
Yes. I would like to know a bit more about how you built this best VRF product. Do you then start from several top of atmosphere images, and how do you use the radiative transfer models then?
This is using MODIS surface reflectance products already. Okay, but the idea is to then, we're starting from kind of slightly cheating perspective. You could do it. You could couple it to an atmospheric model to produce top of atmosphere. As a demonstration, the idea was to take observations that are still contaminated by clouds and snow and combine them in this filtering process to remove, so that the land surface model, the radiative transfer model, if you like, is a linear BRDF model that predicts what the surface reflectance ought to look like based on what we have, the observations already. And so it predicts what the surface will look like tomorrow from what we know about today and yesterday. And then if it departs from that, then something's happened. Either there's been a change, and if it's a sudden departure, then it's clouds or snow. And so it's allowing us to identify those. So that, if you like, that's the kind of first stage. But you can move that up to top of atmosphere quite simply. Well, I say quite simply, relatively. Just a very quick plug. Sorry, this is this is a QA for ECV project. Could people have a look at it? Anyone interested in this is a survey for QA that is being funded by the EU, and we've been asked to kind of put this out to the user community. So there's a questionnaire, and you can win prizes. So please respond to the questionnaire. What are the things that we need for QA for climate variables from Earth observation? Just thought I'd raise that.
One more. I'm going to say something provocative. You should feel free to disagree with.
Okay. I disagree.
It's the idea of propagating information through these pre-processing models to get, say, a per pixel uncertainty on the VRF is a lovely example. I think it's really hard to capture the systematic uncertainties that you introduce in those processes in any reasonable way of representing the posterior uncertainty of that product that you're then going to use as the data uncertainty on the next level down. And it's one of the reasons why, unless there are strong operational time constraints, I wouldn't recommend in general doing these pre-processing steps separately. Sure, you propagate the uncertainty, but it's very hard to represent the systematics of that uncertainty in these separated steps. If you do it as a single process, you get that automatically.
I would agree. I don't disagree. I guess the issue is doing it as a whole. So in doing it as a whole thing, you have to do the atmosphere, you have to do the parameter retrieval, and you have to characterise the uncertainty. You know, in all of those things, ideally, to understand where any big uncertainty. If there are problems, in a sense, doing it bit by bit to start with, maybe we can identify where there are, what we know best, and maybe where we don't know things. But ultimately, yes, you'd like to be able to do the whole thing in one go and just chuck in and have all the kind of coupled surface, atmosphere retrievals. And I think there's no reason you can't do that. At the moment, it's just complexity and the fact that we haven't really got round to doing it.
Yeah, I agree.
But, you know, we should definitely do that.